Today, I'm going to be discussing the red-black tree. It is a data structure that is similar to a binary tree, but it has certain properties that allow for more efficient operations and offers advantages in terms of the time complexity as compared to a binary search tree. What is a red-black tree? It is essentially a self-balancing binary search tree. It maintains two colors, a red and a black, to color its nodes in order to maintain the properties of a red-black tree that allows for efficient insertions, deletions, and allows for efficient data retrieval. One of the drawbacks of using a binary tree or a binary search tree is that a lot of times it can become very unbalanced and can essentially take the form of a very long linked list instead of maintaining a tree structure like shown in the slide. So a red-black tree basically, it essentially allows us to, whenever we perform operations such as inserting nodes or removing nodes, to rebalance and allow for efficient search time that is proportional to the height of the tree rather than the number of nodes within the tree. In order to maintain a red-black tree and maintain its self-balancing properties, the following attributes listed below must be followed. Every node must be either a red or a black node within the tree, and the root of the tree must always remain black. No two adjacent red nodes, essentially meaning that a parent node cannot be red if the child node is red. This will break one of the tree properties. And also, from any node, the same number of black nodes must, in any given path, must all be evenly distributed. We cannot have, let's say, 4 black nodes stemming from one node and then 3 black nodes stemming from the left subtree of that node, because that would mean that the tree is imbalanced. And all leaves, or in this case, nil nodes, must be black. I'm going to highlight some key differences between a valid red-black tree and an invalid red-black tree, and these will show how the invalid red-black tree will break the properties while the valid red-black tree maintains the properties, as discussed earlier. As you can see here, we have a red-black tree. It is easily identifiable as a red-black tree because of the red and black nodes present on the screen. But in order to be a valid red-black tree, we must first ensure that all properties are being met. As we can see, the root of the tree is a black node. And then we also see that there are no red nodes that have any children red nodes. Then we need to also check if the same number of black nodes are in each given path. Starting at the top of the tree and going down to 10 and then 1, we count 3. We go down from 16 to 10, then 15, that's 3, 16, 10, 7, 3, 16, 25, 18, 3, 16, 25, 30, 3, 16, 25, 60 tree. So we see that the black depth is maintained throughout the entire tree. And every single root, every single leaf node is in fact a nil node, since the leaf nodes at the end are trailing off into nil nodes. And then when examining an invalid red-black tree example, there are a couple of things to highlight right here. First, in the left tree, we see that the nodes 70 and 80 already invalidate this red-black tree. We would need to perform some recoloring and rotations, which we will get into here in a little bit, in order to maintain the validity of this red-black tree. So, as you can remember, no red node can have any red children. And then on the right side, it is a little harder to spot at first, but if you count in descending order from 1610 to 1, and then 1610 15, 1610 7, we see that it begins to average a black depth of 3 black nodes starting from the root node. But if you go to the far right, where it goes 16, 25, 60, 70, that shows 4 black nodes within that path. And as you can remember, the same number of black nodes within any given path from any node must be the same. So the right tree is not a valid binary or red-black tree. So whenever we get into situations where a child node becomes too heavy or the colors get imbalanced, we can perform rotations in order to maintain the red-black tree property. For example, if we have 10, 6, and 4, this could mean that the colors are imbalanced, and if we have a red node, or an uneven number of black nodes within a given path, we can perform a right rotation, which takes 6, the median, the middle node, and, and left rotates in order to get a balanced red-black tree. And we can do the same on the right, where we rotate right around 6, the median. Now, in certain situations, we may need to perform 2 rotations in a row. For example, we have a unbalanced red-black tree that we need to perform a left and then a right rotation. And as you remember earlier, a left rotation will rotate left around the median. And that gives us 10, 6, and 4. Then we need to, in order to maintain the red-black tree property, rotate one more time. This would be a right rotate around 6, the median. And as you can see, we finished our rotations and we have maintained the different properties. Now we have here this pseudocode in order to insert nodes into a tree. If the tree is empty, create the new node with the color black and set it as a root. Else, we are going to insert the new nodes as leaves with the color red after finding the correct place for insertions. If the parent of the new node is black, we would exit because we can have a black node then a red node. But if not, then we need to check the uncle. If it's black, we need to rotate and recolor to maintain the red-black tree property, as shown by the rotations earlier. If the uncle of the new node is red, then we need to recolor and then check the grandparent of the new node, essentially becoming our current node in which to check step 4 again. So a red-black tree provides balance, allowing us to perform efficient operations relative to the height of the tree. So time complexities within the realm of O of log n, and it avoids the O of n linear time complexity, but it does add the extra overhead of complex operations and complex maintenance whenever modifying the binary or the red-black tree, as opposed to a standard binary search tree.